Okay, we want to talk about something called correlation, and I'm going to be using things out of both books. So we'll start with the Green and Salcombe book tonight, and we will also be using a little more of SPSS. So again, I don't know how many of you have bought the SPSS package through either the On the Hub or some other way, or how many of you have are planning on hoping to get in on the citrus side. I sent you a link that Dr. Lampley produced about how to get that, how to have it open files, and you have to save the file somewhere and go get it somewhere. Anyway, however you need to do that, just do that. I'll try to help you as I can, but I think he gave a pretty good explanation. I'm going to be accessing it a little bit differently because I've got SPSS on this computer. So I'm just going to, I can just click on the files, it just kind of opens up in SPSS, so you'll see that as we go along. But if you look at, so first of all, let's walk through a couple things in the Whit book, starting on page 127. Correlation is one of those weird things that kind of sounds like what it really means. The root part of correlation is relation. So the correlation measures the relationship between variables. That will make sense more in a few minutes, hopefully. A correlation measures the relationship between variables. Let's say, for example, I'll go back, I'll use this example to death, but I think it's easier to then try to give it another context. Let's say that you have taken the ACT and you have taken the SAT. And you've got scores. I've got a bunch of people who took both tests. The question I might ask is, are the people who scored high on the SAT the same people generally that scored high on the SAT? If you score high in one, do you also score high in the other? The opposite side of that coin, which is the exact same question, do the people who do lousy in one, are they the same people that do lousy in the other? That's a correlation. You're comparing, the variables are the SAT and the ACT. That's what I mean by a correlation, looking at the relationship between variables. But what if we found out that the people who score really good on the SAT are the ones who score really bad on the ACT? That's still a relationship. It's just the opposite kind of relationship. I'll give you some examples, but let me say to begin with, let me see if I can write on this stuff. A couple things about correlation. Again, statisticians being the unimaginative, uncreative people that we are, we have a letter that stands for correlation. I said the root word is relation. We'll get a number for it, R. Again, kind of makes sense. R measures the relationship. R is we call it the correlation coefficient. It's a number that tells you something about it. The correlation tells you two things. It tells you direction and strength. Correlation numbers are between -1 and +1. So it's going to be plus or minus point something something. Now, do you remember if we were doing those z-scores, the z-score was either positive or negative, depending if it was above or below the mean? That's what I mean by direction. The correlation is either positive or negative, depending on whether, you imagine this, whether the number is positive or negative. So direction is pretty easy to tell. It's just simply plus or minus. Strength also makes sense, but let's be careful the way we put it. Strength is how strong the relationship is. Back to my SAT, ACT example, if it turns out that the people who score high on one tend to be the people who scored high on the other, likewise the people who score low on one tend to score low on the other, then those say the same thing. That is a positive relation. So I'm going to get a positive number. I might get a positive 0.53. It's clear that it's positive, but how strong is it? And the answer is, I don't really know from just looking at the number. Now, when we make SPSS do this stuff, there's ways that we can tell how strong it is, or whether it's, as we were going to say, significantly strong or not. But 0.53 is a particular strength. Let's say I got another correlation of 0.27. They're both positive. Which is stronger? The 0.53 is stronger. Now let me say this the right way. I said a second ago it was critical the way we say it. The correlation, the stronger correlation, isn't necessarily the bigger number like it is here, although that's true in this case. The stronger the correlation is, the further away from zero it is. What's the mathematical term for that? Again, I'm an old overachieving high school math teacher. How about if I get a correlation of a negative 0.73? Which is the strongest correlation now? Yes, the negative 0.73 is the strongest of all the three correlation numbers I gave you. So, because it's furthest away from zero. Mathematically, we use the term absolute value. I used this before, back when we were calculating the standard deviations, the first and only time we did them by hand. I talked about the absolute value being meaning furthest from the mean. This is furthest from zero. So the one that's furthest from zero has the strongest correlation. In this case, it's a negative correlation because it's negative 0.73. So two things, strength and direction. Let's walk through just a couple of examples on page 129, Progress Check 6.1. Some pretty good examples there, and I'm going to give you some more because these are in the book. The statement is made that, let's go back here. Hang on a second. I'm just going to talk through these, so yeah, you have to look at me. Okay. Statement is made that more densely populated areas have higher crime rates. So my two variables are population density and crime rate. If more densely populated areas have higher crime rates, let's just talk about it in terms of direction. Is that a positive or a negative correlation? More densely populated areas have higher crime rates. I would say don't everybody weigh it at once, but yes, everybody weigh it at once. I hear positive. I see positive. It's positive. Is that the same thing as saying less densely Okay, less densely populated areas have lower crime rates. That's also, it's the same thing. I'm saying the same thing. If you're high in one, you're high in the other. If you're low in one, you're low in the other. It's the same thing. It's positive either way. The idea about a positive correlation, it means things are going in the same direction. If you increase one place, you increase the other place. If you decrease one place, you decrease the other. So you're changing consistently the same way. That's a positive correlation. How about example B? School children who often watch TV perform more poorly on academic achievement tests. Our two variables are TV watching and academic achievement. Okay, as one rises, the other falls. Those are inconsistent or opposite directions. So the higher the TV score is, the lower the academic report score is. Vice versa, the lower the TV score is, the higher the academic score is. So that is a negative correlation. Now let me be clear about something, and this is literally one of the most important things I'm going to say in class. Correlation does not mean you have causation. If B is true, that as TV watching rises, test scores fall, that can be perfectly fine and true, and we can document that, we can measure it, we can say whether, here's that word again, significant or not. It does not mean that watching TV has an effect on the academic. Now, it might, I don't know, but just from the correlation, we can't determine that. So correlation does not mean causation. Matter of fact, if you continue to work with me through your program, you will hear me say a number of times that you need to avoid, even in writing your dissertation, you need to avoid causal terms like impact and effect. I can tell if there's a significant relationship, but I can't tell what the cause of that relationship is. Or I can tell, as we'll measure later, I can tell if there's a significant difference, say, between two groups, but I can't tell what the cause of that difference is. I'll go back to that again in a few minutes. Let me go through these other examples first. Heavier automobiles yield poorer gas mileage. What are our variables? What are our variables first? Yeah, you're right. Okay, the automobile weight, how heavy a car is. Okay, good. And the other variable is the gas mileage, which is the other. Well, not just poor gas mileage, but gas mileage is a variable. The heavier the car is, the lower the gas mileage is. Again, in all things being equal, it's not a perfect correlation, so it's not going to be. It's going to be negative, like you said, but it's going to be negative. It's not going to be a negative one. You almost never get a plus or minus one. Unless you're correlating something with itself, of course, and we'll see that in the SPSS output a little later. But does it in this case? Does car weight affect gas mileage? Yes, it does, but not just from the correlation, because we know that if you manipulate that variable in other kind of experiments and other kind of numbers. For example, if I look at the incidence of lung cancer and smoking, I see a positive correlation. Does that mean, does that in it, no, does that, let me be careful how I say that. Does that in itself mean smoking as a cause of lung cancer? No, it does mean itself. However, in that case, we've got enough information from other sources that we're pretty sure that is indeed a causal effect, but not just from the correlation. I'll give you some examples to where you'll see that sort of thing is not necessarily true either in other cases. Better educated people have higher incomes. In general, true. Does that mean education makes you make money? No, I mean, okay, you've all got at least master's degrees. How rich are you? At least, probably not from your salaries, though, unless you've inherited a bunch of money or independently wealthy some other way. Probably doesn't have much. As a matter of fact, it kind of goes down. But in general, better educated people have higher incomes. Not all the way, not all in every case, because we can all name half a dozen people just off the top of our head that had dropped out of high school and are billionaires probably. But your chances of doing that aren't very great. So I wouldn't take that risk. But yeah, a positive correlation. And there's probably some cause behind that, but not just from the correlation. The last example here, more anxious people voluntarily spend more time performing a simple repetitive task. So we've got anxiety and time performing a task. If anxiety increases, it takes you longer to do it. That's probably a positive correlation. Yeah. Let's say you teach in an elementary school. And let's say it's I don't know, K through 6th grade. Or 8th grade. 8th grade is even a better example for this situation. So I go in and I measure a couple of things. I give everybody in your school, 0 through grade 8, I give them the same math test because I'm going to measure their math knowledge. Fair enough? And you're going to get, each person is going to get a score, so I'm going to have a distribution of math knowledge scores. The other thing I'm going to measure is shoe size. So I go in, it sounds silly, which is kind of my point. So I've got 2 pieces of information for each student in your class. I've got how big their feet are, and I've got how much math they know. What do you think I'm going to find? I'm going to find the bigger the feet, the more math they know. Therefore, big feet make you know more math, right? That is, the comment was made, that's what a lot of our commercials are based, and that's exactly right. So again, and commercials are a great source of this kind of true but misleading information. Yes, elementary kids who have bigger feet know more math. They sure do. But why can't we say it's the size of the foot that causes you to know more math? What is it that causes you to know more math? You've been in school longer. Yeah. An 8th grader is going to know more math than a kindergarten does. He's also going to have bigger feet. But there is indeed, I would venture to guess, a significantly strong correlation between feet size and math ability. But there's something else. What happens, though, is A doesn't cause B. Something else causes both A and B. We talked about in another lesson, I think, that things that you have to have if A causes B, A has to happen before B. And we can tell that. And there has to be some kind of statistical significance or relationship between A and B. We can tell that. We can get the correlation of foot size and math ability. And we have to make sure that the third thing is we have to make sure nothing else causes B. Oh, that's our problem. In this case, clearly something else caused B. Not only B, but caused A and B, foot size and math ability. So just, again, I'm underscoring, I'm beating it to death, but it's important that correlation itself does not mean causation. Another example. No, let me continue with this example a little bit more. Let's say we collect the same data from students across campus here. Traditional undergrad students aged 18 to 22 or so. I'm measuring their shoe size and I'm measuring their math ability. What do you think we'd find there in terms of correlation? I wouldn't find much. I'd find people with big feet knew a lot of math, people with little feet knew a lot of math. People with big feet didn't know much. People with little feet didn't. I probably wouldn't find much of a correlation. My correlation would probably be close to 0, plus or minus. Yeah. You say no correlation. That's true. There's going to be like probably a point 0.05 or something, but we're going to say that's not significant. And again, we'll talk about that later. Yeah. So in that case, but I thought bigger feet made you know more math. Well, at some point though, your feet kind of stop growing, but you may still continue to learn math. So the correlation is significant when you have a lot of variation in elementary school because you've got a lot of variation in shoe size, but you don't have much variation here across campus. So there's not a causal relationship. Let's stick with college students for a minute and look at another example. I am measuring two things. I am measuring their GPA. I can get that easy enough from the registrar's office. And I'm measuring how much they drink. How much they drink. So, how much time they spend, you know, at, well, Poor Richard's is closed now, so if you're not from here, that won't mean anything. But the local ones are expressing surprise. Yes, a long time hangout down the street from here. Anyway, yeah, really. So he's surprised too. Anyway, so I could have got this open a couple of months ago. I could have, you know, gone over to Poor Richard's and look to see how much people are drinking, ask them what their GPA is, or look it up later. Like I could really do that, but you know, if you get that piece of information, what kind of correlation do you think you'd find? The more you drink, the higher your alcohol consumption is, the lower your GPA is. We would probably get a significant negative correlation to that. So drinking lowers your GPA, right? Maybe. Probably. But it's possibly likely that instead of A causing B, B causes A. Gee, I'm doing really lousy in class. I think I'll just go down to Poor Richard's and have a few. So it may be that your low GPA actually affects your alcohol consumption. So just because there is a correlation, there may be a causal relationship, but it may be the opposite way than you're thinking. So don't infer much in terms of causation from correlations. I got some more examples. Questions, thoughts, comments so far? Okay. Let me just throw out a couple of pairs of variables, and you tell me if you think it's going to be positive, negative, or not much either way. How about intelligence and academic achievement? The smarter you are, the better your grades are, let's say. Yeah, that's going to be positive. Now, again, we've all known people who were really, really, really smart and flunked out of college, and people you wonder how they could tie their shoes and they made it through. But in general, the smarter people are, the more academic achievement they have. How about academic achievement and hours of watching TV? We put that in the elementary school, but let's take it to the college level. Yeah, probably it's going to be negative, just like it was in our other example. Think about this one. Productivity per acre and value of farmland. Productivity per acre and value of farmland. The more or less corn you grow, let's say, or you can grow. Yeah, I think these are answers to this one. If you're looking at farmland and it will produce more corn, that's going to be higher in value. It's going to be worth more. So that's a positive correlation. Likewise, if it doesn't produce squat, it's probably not going to be worth very much. Or if it doesn't produce squash either. So, stick with it. Total corn production and price per bushel. The more corn you have, the less the price. It's supply and demand, essentially. You got high supply, it's going to be easy to get. On the other hand, if you have low supply, then prices go. And when you see this in the news every day. Oh, I saw right before the Super Bowl, because of some climate weather things, there is a chicken wing shortage. I mean, oh my goodness. So, what do you think that? So the number of chicken wings available are not so much. So what's that going to do to the price? It's going to drive it up. That's a negative correlation against supply and demand. How about body weight and intelligence? Not much either way. Yeah. Now again, if you did this in the elementary school, you might find something because older kids are heavier, they're bigger. But across the board with, no, it's, you know, body weight doesn't have anything to do. There's no significant correlation with intelligence, or certainly no causal effect. How about height and shoe size? Let's change from weight to height. Height and shoe size. Taller people probably have bigger feet. Shorter people probably have smaller feet. That's a positive correlation. How about, yeah, I'm keeping up with you guys weighing in online. Looks like we're doing okay. So keep responding. How about time spent in practice and number of typing errors? Do you still say type anymore? Do we actually type? Does anybody know what a typewriter is anymore? Seen them at the antique stores? Okay. Well, let's say keyboard skills for whatever. Okay, so time in practice, and we'll call it typing errors. So the more time you practice, the more you practice, the fewer the errors. So that is which? A negative correlation. Yeah, negative correlation. You actually taught typing. Wow, cool. Gosh. I have a skill. This is an aside. I learned to do something, as I said a couple of past lives ago, and some of you aren't even going to know what this is. If you have an 8-track tape that's messed up or it drags or something, I can fix it. That is the most useful skill I could possibly think of, but I can do it. It was useful a while. I mean, yeah, give me tape and scissors and a screwdriver to get the box open, you're going to have a good tape if you can find anything to play it on. Anyway, how about, let's stick with this. Shoe size and salary. That's a little bit, not a tricky question. It's a little bit loaded, though. Because of gender. And taller people are viewed more possibly in leadership situations. That's true. Sports, athletes are bigger. Athletes are bigger and have bigger feet than normal people. Generally, they shouldn't have much to do with each other, but again, it's a little bit. So I'm kind of giving you what's kind of on the borderline here. I mean, the textbook answer is no. I mean, by textbook, I mean the standard answer is no. There's not a correlation. But realistically, you know, there's some, and this has to do with some psychological effects like perception, things like that you're bringing out. So, yeah. Basketball players have big feet. If you watch any kind of athletic competition, you'll see, you know, athletes tend to be big people unless you're watching horse racing or something. But I think if you play in the NBA, you probably make more money than if you're, you know, a jockey. But yeah, so there may be I think there probably would be a positive correlation. I'm not sure if it would be significant or not, though. Another couple real quick. Family income and value of the home. More money you make, probably the more expensive house you live in. The less money you make, probably the less expensive house you live in. So that'd be a positive correlation. And I know you're going to call me on this next one, so I'm ready for you to. Age of an automobile and trade-in value. In general. How old your car is and how much it's worth. In general, that's a negative correlation. Now, what you're going to say, and I'm going to say it before you do, what if you've got an antique car that's worth a lot of money? Yes, there are some of those, but in general, but that does make it not a perfect correlation. You got some old cars that are worth more than some new cars, but in general, the newer cars are worth more than the older cars. So that's kind of a good example of that. Okay. Other questions, thoughts, comments about this so far? All right. So, look on page 131. Top page, and that's kind of where we are. So 131. I want to draw more for you here in a minute. You remember I said something about high school algebra graphing in a previous lesson, and that's kind of what I want to talk about here again. So if you look at these things, You got 6 figures on page 131, and they're called scatter plots. Or sometimes you see them called scattergrams, or even I've seen them scatter graphs. So remember I talked about when you did the graphs, we divided the graph up into quadrants. I said this is essentially we're dealing in the first quadrant. That's true. So I'm looking at something like height and weight. I've got 2 pieces of data from each person. I've got their height and I've got their weight. So I've got someone say with this height, oops, didn't mean to do that. Okay. So the person has this height because the dot's over where it is on the scale of height, and that particular person has this weight. So one dot represents 2 pieces of information because we have 2 axes. In the Cartesian coordinate system, we talk about the x-axis and the y-axis. We talk about the same thing here too. So this is x. X is the horizontal axis. It's essentially like a number line or a scale. And weight, in this case, is our y-axis, or it's also a number line or scale. So x runs horizontally, y runs vertically. So one dot gives you a location on each of the 2 axes. So I've got height and weight for a bunch of people. So I'm going to have something like this. So notice some shorter people weigh more than some even shorter people. So some taller people weigh more than less than some shorter. Anyway, so I've got this scatter plot. Now I've got a little bit of a pattern here. So if I kind of look at the scattering plot sort of holistically, I can kind of see that they kind of fall within that kind of figure. It kind of leans from lower left to upper right. Now, do you remember graphing lines in Algebra 1 again? And remember there was something called a slope of a line. And there's a characteristic about slopes of lines that's the exact same thing as we're talking about here. First of all, a slope is either positive or negative. Just exactly like a correlation is either positive or negative. And it works exactly the same way. So sure enough, your Algebra 1 stuff actually really honestly did mean something. So because this leans and this way, for me, this way, that would be, if it were a line, it would be have a positive slope. If it's a correlation, it is a positive correlation. If you're lower in height, you tend to be lower in weight, down on this lower left end. If you're higher in height, you tend to be higher in weight. Not everybody, not absolutely, but that would be at the upper right, and that's a positive slope. Now let me take that a little bit of a step further before we get into the mechanics of the correlation. And I've got 2 dimensions here. When I had one set of numbers, one distribution, I could calculate the mean, median, and mode and standard deviation for that one set of numbers. Now I've got 2 of them. So this in particular kind of clusters around this line going, in this case, from lower left to upper right. Some are above and left of that line. Some are below and right of that line. A couple of them are real close to it. I don't think I've got anything that's really right on it, but a couple are pretty close. That is called, if you look at your syllabus, it talks about correlation, which I've been on for a while now. That is called the line of regression. So correlation feeds into what we call regression analysis. Okay, there's a term that is not very intuitive. Unlike the term correlation, it's kind of intuitive. A line of regression, and we're talking about regression analysis. Now keep in mind that we're not talking about causation, but here's what we can talk about. We can talk about prediction. So regression analysis allows us to predict. For example, if I had someone at this height, I could predict what that person's weight is by doing this. Going up to where I hit the line and seeing where that falls on the weight scale. If I had a person with this height, I would predict he would have this weight. Now I've got a couple people with that height. So for example, I've got this person and this person. They are about that height. One of them's a lot heavier than the other is. That's because of the idea of variability. So it's an okay predictor, but it's not a perfect predictor. The closest I have is probably this guy here. He's pretty close to both the height and predicted weight. So okay, so I would have been pretty close predicting him. But if it's somebody else, I would predict a certain weight, then he may or may not. He's probably going to be somewhere between here, between that weight. It's pretty widespread. So the stronger your correlation is, the tighter that scatter plot's going to show in terms of the pattern of the dots. So I'm not going to get as much variation in terms of what I might predict. Does that make sense? I'll say a lot more about it as we go along, but we're kind of okay with that so far. Now, again, I'm jumping ahead of myself, but I'm going to come back full circle. But let me go a little bit further with this line of regression in terms of how you use it. So let's say we know what the correlation is. We know it's 0.35 or 0.82 or whatever. We know what the correlation is. That tells us, well, it's a positive correlation because it's a positive number, but it tells us strength also. Again, the further away from zero, the stronger the correlation, the better predictor that variable is. One variable is for another. So, remember, gee, good, you're teaching high school algebra 1 again. That's hard to get away from. Remember one of the ways that we wrote the equation for lines? And there are a couple of forms of it. So if you can type in the symbols at home if you want to respond that way, that's fine too. But what's the basic? One of the basic forms. There are a couple of them, like I say. But what's one of the basic forms of the equation for a line? You'll remember this, or you'll remember that that sort of thing exists. I've got x's and y's here. How do I express one in terms of the other? In this case, I was using x to predict y, right? So my y is expected to be equal to something. Y equals something. Ah, yeah, okay, it's on the screen. Y equals mx plus b. So if I know what m and b are, I can take a number x and predict what y is going to be, or tell what y is going to be if it's on the exact line. This is an example, or it's not an example of, but the regression equation. I usually don't deal with regression much until the next course. But again, this is an introduction to regression. If I know what m and b are, if I know what the other two variables are, I can plug in x and I can tell what y is supposed to be. So if I'm predicting from this height, I'm going to plug that height in some equation and I'm going to get out what this weight is. Now again, that may be right on the money, or it may be way off this way, or it may be way off this way. But that's regression analysis. I want to go back into more of the mechanics of or the workings of correlation, but does that kind of make sense in terms of how we use it? Not to determine causation, but to determine prediction. College admissions, for example. We want the students who are going to be successful. How do we tell, or what data do we use to tell if our students are likely to be successful? I've already mentioned a bunch of it. Test scores, for example. We use things like the ACT. Is it true that ACT is a good predictor of college success? And the answer is, sometimes not. Again, we all know people who knocked the top out of the ACT test and couldn't pass freshman English. We know people that you're surprised they spelled their name right and they were graduated 4.0. But in general, people who make higher ACT scores tend to make higher college GPAs in general. So it's a predictor. It's not perfect, but it's about as good as anything else you can come up with. What's another thing that we use to predict college success, or in terms of our admission decision? Okay, high school GPA. How were your grades in high school? People who made good grades in high school tend to be the ones who make good grades in college. It's not perfect. You got guys like me who made really good grades in high school, and I got to college. I enjoyed college. My GPA shows it for the first 2 years. And you get some weird things like, again, and I used to work in this area a little bit, but there are some reasons for that. So it's not a perfect correlation. There are some reasons with high high school GPAs. Sometimes you'll low college GPAs because you get, in my case, I made good grades in high school, never had to study, never learned to study. Get to college, well, I'm going to be brilliant there too, right? No. Oh, you got to study. Guess I better figure out how to do that. It took me a couple of years to figure that out. So there are a lot of variability within this. I figure for the grades I actually did make in college my first couple of years, I must have been a genius for as little work as I put into it. Scrape those C's and D's out. So is there a way, and again I'm thinking sneak preview of coming attractions down the road, not necessarily even this course, but maybe we could combine things like high school GPA and ACT score. Maybe we can put those together somehow and get more of a composite prediction. That's called, I'm not even going to write this down, that's called multiple regression, when you have more than one predictor. Multiple regression. Now I can only draw things on 2 dimensions on the flat screen here, but I would have to have a third dimension to include another variable. Or you know what, you might want to use 4 or 5 or 6 or 10 variables to predict something. Some variables are going to be better predictors than others. Right now, I'm just sticking with the one variable. So simple regression is what we call when we use one variable to predict another variable. But that's based on correlation. Let me come back full circle and talk more about correlation a little bit. Again, looking at the drawings on 131, just to continue to talk through those. If you look at the very first, well, the top 3, you see a positive correlation, you see a negative correlation, you see how those kind of things tend to lean toward one way or the other, and you see one where it doesn't seem to lean much way at all. Not much of a correlation. In that case, height and life expectancy. So how tall you are doesn't seem to make much of a difference in terms of how long you live. They don't seem to be linked together. So not much of a correlation. The bottom 3 you see are all positive correlations. But the bottom 3 you can see visually something about strength. Now number-wise, you see 3 scatter plots for 3 correlations. One is an R of 0.27. Then an R of 0.50, and then an R of 0.75. And the higher the correlation, the closer the dots are together. Therefore, the stronger correlation. And don't have it here, but we could draw lines of regression through those things. Now, sometimes you get a situation like this. Let's say my 2 variables are anxiety. Let's say I could draw better than this too. That's a stretch. Anxiety and test performance. Anxiety and test performance. Let's look at that relationship. Let's see what we might kind of expect to get. My anxiety level is so low. Oh, gee, I got this test coming up. Well, who gives a flip? I'll just show up and see what happens. Whatever. Where do you think that dot's going to be? Probably so. Low anxiety, probably pretty low test performance. Yeah, not going to worry about it, not going to think about it, not going to take it seriously. I'm not anxious at all. Well, you know what? Maybe you should be a little bit, because I'm a little more anxious. Hey, I think I'll study. Heaven forbid. I'm a little more anxious. That's going to induce me to study more. So I'm probably going to make a little better on my test. So if I raise my anxiety a little, I'm going to start to get things like this, which starts to look pretty positive, doesn't it? What happens? Oh, I'm just so anxious. I'm worried about the world's going to end. I'm going to fall apart. What happens? How's my test score going to be there? I'm going to be paralyzed. If I have a lot of anxiety, I'm going to be back down here again in test performance. So I'm probably going to see something like this. And my pattern, I can identify it by that. That's called a curvilinear relationship. What do you think the overall R value would be close to if I take the whole thing? Yeah, the overall R value is going to be close to 0. But is it really fair to say there's not much of a correlation? The answer is no, not really. Well, what kind of correlation is it? Well, the answer is that it depends. As with the answer to most things in life is, it depends. If you're talking about low to mid anxiety, there's a positive relationship. If you're talking about mid to high anxiety, there's a negative relationship. So there is a significant correlation, but it doesn't come out just in the R value. That's why, and we're not going to get into this other than me saying it, that's why sometimes we talk about partial correlations. If I'm talking about the correlation of anxiety from here to here on anxiety, it's going to be one thing. If I'm going to talk about anxiety from the midpoint on up, it's going to be the exact opposite thing. So we may talk about partial correlations. That's all I'm going to say about that, like Forrest Gump says. You've got an example of another scatter plot for a curvilinear relationship on the bottom of 132. The variables are the relationship between age and physical strength. Real young people aren't very strong. Real old people aren't very strong. So it kind of peaks and then it goes back down. Now, curvilinear relationship might look like that, or it might look like that also, depending on what your variables are. Questions, thoughts, comments? Let's look at a couple of real-world examples. If you want to, if we were going to do this by hand, there are a number of formulas to look at correlation. Here's one of them. The value of R is equal to come on, Don. Oh, you having trouble following? Any questions? So we just raised the anxiety level. Ready to take a test? Okay. You want to do this? I sure as heck don't. But I do want to look at it for a little bit. Now, this looks awful. And I can just read your mind with the words you're thinking right now, as you just shouldn't say in public. But let's look at it. Let's look at the little pieces. What are the letters I have here? The variables. I've got N, I've got X, I've got Y. That's all I've got. I have only 3 variables here. And we know what every one of them is, and we know what to do with every one of them. Let's look at a couple pieces here. Sigma XY, you multiply them together and you add what you've got. We've done that. Sigma X times sigma Y. Add all the X's together, multiply that by the sum of all the Y's. We've done that. Oops. Sorry, I left off my parentheses. I knew that's what was bothering you. Square the X's and add what you've got. Add all the squares together. We've done that. Add the X's together, then square that. We've done that. Let's do the same thing with the Y's. We've done that. It's a messy formula, but it's not complicated. We've done every part of this. It looks messy because we've got 2 variables, an X and a Y, instead of just an X. And again, we've added and squared. We've squared, then we've added. That's all there is. That's all there is to it. So I meant for it to scary. It worked, but it's not scary. I still don't want to do it. Now they've got some other formulas in the book that you also do not have to worry about. Let's look at, walk through with me an example. Now, let me tell you something about this book if you haven't figured it out already. This book has great information, wonderful examples. They're presented, some of them are presented in the worst order I can imagine, because what it will do, it'll give you this example, this problem, and then it'll start working out 5 pages later. And it'll give you the answer 7 pages later. And it'll tell you 3 pages later what you need to do to get the answer they used 7 pages earlier. So the sequence is, but I know that. I can make it work. If you're reading through this for the first time, it's going to drive you crazy. Be prepared for that. Well, how did I know to get this? Because I hadn't talked about it yet. That's right. That's the way it works. All right, so go back to page 128. Chart on the upper left. I want to know if there's any correlation between the number of greeting cards you send out and the number of greeting cards that people send to you. Now, this is an artificially small sample size, of course, but that's it's a good teaching example. So, Andrea sent 5, received 10. Mike sent 7, received 12, and so forth. I want to know if the more you send, the more you get. I want to know if that's true or not. That's the basic problem. I don't know. But I know on page 14 pages later, on page 142, I've got where they work all this stuff out by hand, and it tells me that R is 0.80. So there's a positive relation. That means the more you send, the more you get. Is that a significant positive? Is it a significant relationship or not? I don't know from this. Let's do this same problem the lazy shortcut way. Any objections to that? No. Okay. Here's what I'm going to do. I'm going to call up SPSS, a blank SPSS, and we've talked a little bit about how you get data in here. So let's use this for another example. and I'm going to add my data to this SPSS sort of spreadsheet format. So the first thing I do to set it up, I have to click on Variable View. Now, if you've got SPSS in front of you, work through this with me. If you don't, work through it when you're watching the recording. Again, let me repeat my suggestion. Yeah, it's not real fast sometimes. Yeah, let me repeat my suggestion that it's good to have two devices to do this with. One that you're watching what I'm saying now and what I'm demonstrating, the other to actually do it. So if you've got an iPad or a laptop that you can put by your desktop or whatever, that's the best thing to do. Otherwise, it's hard to see this on one screen. Or if you've got a double screen set up, then you can use one screen for each. But right now, what I want to look at specifically is a bunch of blank rows and columns on SPSS. So the first thing I have to do is I'm going to click on Variable View, and I get something that doesn't look much different than what I had before. Are you up yet? Okay, well that helps. Yeah, she accidentally turned off her computer. Yeah, that'll take a minute. Has anybody gone to the Citrix site and used that? Yeah, you can. This is a good test if you go to the xen.etsu.edu. Again, I've sent you directions on all that, and you can call up SPSS. Okay. Okay. All right. So I'm going to Variable View, and I'm going to name my variables. I want to know something about how many cards we sent, and I want to know how many cards we received. So sent is one variable, received is the other variable. Again, remember, click off that cell so it knows that you're through with it, and it'll fill out the rest of each row with default information. I'm not going to worry about the students' names right now. You could put in a first column with the names or their person number or whatever, but that's not my point right now. So those are my two variables. Now what's going to happen when I click on Data View, those variables are going to become column headings. Voila, there they are, column headings. So person number one, that's just, you can see the one beside that. That's just, if you resort these, it won't be the same person in the rows necessarily, but it doesn't matter to me right now. Person number one happens to be Doris. She sent 13 cards, and she received 14 cards. Person number two, which happens to be Steve. Steve sent 9 cards. He received 18 cards. And so forth. Mike with 7 and 12. Next one is 5 and 10. And the last one, John sent 1, got 6. Again, click off the last cell. So I've got my data looking pretty much like the book shows it to me, especially back on page 120, whatever that was, 128. They've got a bunch of columns on the example on page 142 because they did all this formula stuff that I'm not going to do. So I'm ready to run the analysis. Where do you suppose, again, where do we start if we're going to analyze? Speaking of things that are intuitive, analyze. Okay, I'm going to analyze, and you'll see that when I click on the drop-down menu below Analyze, I see an option called Correlate. We want to get a correlation, we're going to correlate. And you'll see beside that 3 different options. 2 of them we've kind of talked about already, bivariate and partial. And this I'm not going to worry about, but all the ones we're going to do right now are bivariate. That means you're handling 2 variables at a time, bivariate, bi meaning 2. So when I go over and I select bivariate, I'm going to get another window to open that's going to have 2 boxes, one on the left, one on the right. There they are. Now notice the couple of the boxes. Again, this is the same case we've seen before. The box on the left has every variable we've got. I'm going to select the variables we want to talk about and put those on the right. In this case, it's both of them. Notice a couple other things. The correlation coefficients, there are 3 options here. The default value is to Pearson. That's the one we're going to use. Excuse me, I do want to say just a word or two about Spearman. Now, the kind of data we've got is, 0 to whatever number. That's good interval or even ratio data. It's ratio data. So again, most of the stuff we're going to analyze is at least interval data. Pearson's what you want to use with that. If we had only ordinal data, we would want to use Spearman. So all I want to say is that if you're using ordinal data, we're not going to do any examples like that. I'm just going to say it. If you're working on your correlation where you've got some ordinal data, we'll do that. It's actually simpler than Pearson because it's lower level data, but we want Pearson. I've talked about 1 and 2 tails a little bit already. Defaults to 2 tail, that's what we want. I want to click on. I want to have both sent and received. Again, you can select and use the arrow. I can just double click everything. I don't think I want anything here. Yeah, I do. Okay, so I'm going to correlate sent and received. If I go to options, for the first line, I want the means and standard deviation. I want to know what the average number of letters sent was. I want to know what the average number of cards received was. I want means and standard deviations. I'm not going to worry about cross-product deviations or covariances. That's next course stuff. In terms of missing values, there are a couple ways we handle missing values. We don't have any here, but if you had some, one way is to just, well, if you got something missing, you just don't include it. That's what this defaults to. There are other ways that we're not going to worry about right now mainly because we don't have any. So, but I do want to get means and standard deviations. Mention is a variable if you has auto fill in the first row. So yeah, that's true. Yeah, it fills out the rest of it for you. If you don't like what it fills out, you can change it. So I'm going to continue. One more thing, flag significant correlations. I'm going to talk about that in a minute. So I'm going to click OK. What happens when I click OK is that I get an output window. So ready, go, set. Now, let's notice a couple things. Do not write with this pen on the computer screen. Write with this pen on the computer screen, okay. All right. The first table. People send an average of 7. People receive an average of 12. And I've got the standard deviation of 7 with a standard deviation of 4.4. Hey, my 12 actually have the same standard deviation. Coincidence. N is 5 for both. When you're doing a correlation, N is going to be 5 for both because you have to have data in pairs. If you have any leftovers, that's when you have the missing data and you're going to throw it out. The bottom matrix, the bottom chart. Notice I've got some duplicate information here. Of these 4 cells, come on, Don. Notice the top left and the bottom right are the same, and they're 1s and 5s. That's because the correlation that this cell has, the one I'm circling, the sent and sent, when you correlate something with itself, you're going to get a correlation of 1. If you sent 5, you sent 5. If you sent 3, you sent 3. So my upper left to lower right diagonal is always going to be 1s. Now the other 2 boxes, lower left and upper right, they're also going to be duplicate information. I wish they wouldn't give you both boxes. I wish they'd just give you either the upper right or the lower left. I'm going to talk mostly about the lower left because some programs will give you what we refer to as the lower triangle. And if we have more than one pair of correlations we're doing, that you'll get more than just one box. But if we look at this, I see 3 numbers here. The 0.8, that's by correlation. Does that sound familiar? That's the exact thing they cranked out on page 142. So R is equal to 0.8 or 0.80. That's a positive correlation. N is 5. That's pretty clear. 5 because we have 5 pairs. Now remember we talked about, it doesn't show up here, but we talked about something called degrees of freedom a couple lessons ago. Degrees of freedom is based on n minus 1. When we're dealing with pairs, it's the number of pairs minus 1. So my degrees of freedom, df, is going to be based on that n, which is the number of pairs, 5 minus 1. I'm going to have 4 degrees of freedom. Now, I've conveniently skipped over one of the numbers because I want to belabor the point on that a little bit. SIG, two-tail. SIG stands for significant. I've been using that word a lot. Let me tell you what it means or doesn't mean, then I'll talk about it. I know that 0.80 is a positive correlation, but it's not a strong or a significant correlation. Because I know, here's how you tell. There is significance if this number is less than 0.05. This is called the p-value. I wish they just used the letter p there instead of significance. P is equal to, if I can get it right, I'll show you. P is equal to 0.104. Okay, I'm going to ask you to walk by faith for just a little bit, and then the scales will fall from your eyes pretty soon, and it'll make sense. But for right now, my line in the sand is it's significant if P is less than 0.05. Let that sink in just a second. Now, here's that's what it means. Here is why it means what it means. The question is, and one of the questions is, in addition to the is it positive or negative, is it strong or is it significant? Think of P as standing for probability. We're going to talk about probability a little later down the road. P is the probability that it's not significant. Therefore, a lower p-value, excuse me, sorry, cough right in the middle of all the drama, the cliff-hanging drama there. P is the probability that something is not significant. Therefore, the lower that p-value is, the more likely that it is significant. You know, with an N of 5, you get what looks like a pretty high correlation. You know, it's only 5. When you've got such a low N, it's going to take a higher R value to be more significant. If this were an N of 500, that 80 would be probably really strong. But when we just kind of handpicked a couple, you might have handpicked a couple on the same side of things. The lower the N is, the more likely that is to happen. If you've got a bag of marbles with 100 blue marbles and 100 red marbles, if you just pick out 2 marbles, you're pretty likely to pick out the same color marbles. So you're going to say, well, looks like the marbles are blue because you picked out 2 blue marbles. But if you pick out 20, it's not going to be likely that they're all the same color. So the larger the N is, the more likely that this is kind of the way it looks. It's not that it's a common occurrence. I told you I'd use the word common. The words common and rare pretty often. So with the small N, it's going to be hard to say that's really very rare. All right, P is 0.104. There's a 10.4% chance it's not significant. So if I'm claiming it's significant, There's a more than a 10% chance I'm wrong. I am not willing to take a 10% chance of being wrong. What I am willing to take, and this is just kind of standard, I am willing to take a 5% or less chance of being wrong. That's why I said 0.05 a minute ago. So this is I would call this a weak positive correlation. Weak positive. Question? If the SIG number of the p-value is less than 0.05, that means, okay, if you're going to say it's significant, you've got a less than 5% chance of that being wrong. Okay, I'm willing to take that chance. Kind of the standard line in the sand for educational research. I will talk more about p-values and alpha levels, but I just need to introduce this to you right now. Let me tell you, part of the way you're going to communicate this, and this is going to be a sneak preview of the coming attraction too. One of the things we'll talk about in the second half of the class, we'll talk about communicating results in APA style. The heart of what I want to say, if I were communicating this in APA style, I'm going to say that R parentheses 4 equals 0.80, P is 0.104. And I don't like that. I'm going to put something else here too. Let me just erase all this mess. R parentheses 4 equals 0.80, P equals 0.104, and just kind of good way of doing things. It's not wrong, but you don't see everybody do it anywhere. I'm going to put comma NS for not significant. Where does the 4 come from? I just erased it. 4 is the degrees of freedom. So your statistic is R. That's why you're saying R. So your correlation for 4 degrees of freedom, in this case, is 0.80. The p-value is 0.104, but that's not good enough. Not good enough, I mean low enough. There's too much of a chance of being wrong that I'm not willing to take that chance of making a claim that this is significant. It probably is. There's almost a 90% chance it is, but that's not a high enough chance of being right. So that's a little bit of the introduction to p-value. Have a lot more to say about it later, but I do want to using another example or two while we've got things going here. Any questions, thoughts so far? Okay, I want to do an example or two from the Green and Salkin book, and I want to go to lesson 31. Begins on page 257. And I want you to call up, again, either do it now with me or do it when you're watching the recording for the first time or, again, later. I want you to call up lesson 31, data file 1. Lesson 31, data file 1. I have put it on D2L, but I don't think you can just click on it from D2L and get it to open up. I think you got to save it somewhere and open it other ways. If you have SPSS on your computer, it might work if you just double click on it. Yes, it may show up like I've got it here. So let me give you a minute to do that. Yeah, you should know by now how long you're expected to suffer from this cold. So, well, when you get to 96 hours. It's less than 31 data 1, yes. You'll see less than 31 data 1, you'll see less than 31 exercise 1, and less than 31 exercise 2. Right now we'll just focus on data 1. Is it opening up? Yay, okay. Now if you're doing it on Citrix, do whatever Dr. Lampley said. At any rate, when you get there, it's going to look like this. Now, open your hymnals to number 257, please, in the softcover book, the Green Falcon. And you've got a couple of scenarios there, and the one I want us to look at is the one that begins on the bottom of that page. On the bottom of 257, it says study with correlations using 3 or more variables. So we're going to do the same thing we did a minute ago. It's just I'm going to have more than 2 variables at a time, and we're going to see what that looks like. So if you'll read the scenario there in italics, it says, John wants to know whether people who have a positive view of themselves in one aspect tend to have a positive view in other aspects. So we're looking at measures on 4 different scales. 1, 2, 3. 5 scales, yeah. 4 scales are questions about how competent they are in particular areas in terms of intimate relationship, relationships with friends, common sense, academic self-confidence, and then just kind of general self-confidence. And you'll see those defined and described on page 259. Little chart there, data set. So I want to know if you're high in one, do you tend to be high in some of the others, or any one of the others? If you look at the research question, and I'm going to stress research questions a little later in the case when we give you examples of how to communicate these things. But there's always a section called the research question, and sometimes they'll give you more than one format of that, and I'll probably stress one or the other. In this case, just the last part of that paragraph is a good research question. Do men who feel confident in one life domain tend to feel confident in the other domains? That right there is a pretty good research question. Or you could say, is there a significant correlation between any of the measures of self-confidence, or any of these 5 measures of self-confidence? Here's the great thing about this Pearson book. It tells you exactly what buttons to push, how to hold your mouth, everything step by step. And we're going to do exactly what we did with the example from the WIT book a few minutes ago. But if you look on page 260, it tells you where to go, what to do, and what it looks like. So I'm going to go to Analyze. You know, it says go to Analyze. I'm going to go to Correlate. We already knew that. It said go to Correlate. I'm going to go to Bivariate. Now, even though we have 5 variables, it's still bivariate because you're looking at the possible pairs between them. For example, is intimate relationship, self-confidence significantly related to common sense, self-assurance? So it's still bivariate. I said everything we're going to do for right now is going to be bivariate. Now, it opens up that box we talked about with the left window and the right. Opens up the window with the left and right boxes. Gives me all the variables. I want all of them. So we've talked about ways to get them over there. So I'm going to select all of them. I'm going to be lazy and just select them all at once and move them over with the arrow. You could double-click each one individually if you want to. But I want correlation with all of these things. It says make sure Pearson is checked. It's going to be because that's the default option. Let me make sure I'm doing it in the order they tell you. It says flag significant correlation. That has to do when the p-value is less than 0.05. It'll give you a little star there and say, hey, this means something. This is a big deal. Click Options. And I'm going to select means and standard deviations. I think that's all it wants to do. Yeah, that's all that. And sometimes I may do a little bit differently than they tell you here, but I'm doing exactly what they say right now. So I click means and standard deviations because I want the means of each of these 5 scales. Continue. It says make sure 2 tails is checked. It is. That's the default value for that too. I'm going to click OK and get my output win. It's going to be a little more complex than the previous one because I've got a lot more variables. Can't look at everything at once. Okay, here are the means and standard deviations for each of the 5 variables. The intimate variable had a mean of 50, standard deviation of 6 something. Friends had a mean of 53. So that means they're more confident with friends than intimate relationships. I don't know if that's a significant difference or not, but it's a little higher. So we typically report means and standard deviations. In my correlation box, see if I can open up this just a little wider. Okay, all right, good. Notice, again, I've got from the upper left to the lower rights. Notice I got a bunch of 1s there. And the upper right is the mirror image of the lower left, duplicate information. I'm going to focus on the lower left. I used the phrase a minute ago, the lower triangle. This makes a little more sense. You can kind of see it is more of a triangular shape. So, the correlation between friends and intimate relationship is this box. That's the same exact information you get in this box. I'm just not going to worry about this stuff. I'm going to look at the lower triangle. So my Pearson correlation is 0.552. Is that a significant relationship? Is that 0.552 that I've circled, is that a significant correlation? And there are 2 ways you can tell. One way you can tell by whether there's a little star there or not. Now, okay, but so if there is a star there, why is there a star there? Or if there's not one there, why isn't it there? It's not significant if it doesn't have a star. This has a star. How could you tell it's significant without the star? It is. We've determined it is significant, but we should be able to tell if it's a significantly strong positive relationship, even if there wasn't a star there. Because look at the other numbers in the box, and not the 80. That kind of narrows it down. What is the p-value? Even though it doesn't label it as p, it says zeros. That's as strong as you can get because it's less than 0.05. Now, let me tell you something. This is a good place to say this. P is never 0. It's just that in this case, it shows zeros because it can only go out to 5 to 3 decimal places. We're never going to say P is equal to 0. Instead, P equals 0. No. Oh, here I can do it. I can do better than that. P equals 0. No. What we say instead is that P is less than, that's supposed to be less than 0.001, or you can even say less than 0.01. P is never 0 because remember, P is the chance of being wrong. What's a nice way to say this? There's not never a chance of being wrong. There's always a chance of being wrong. So your chance of being wrong is never 0. 0 means there's no chance of being wrong. Yes, there is. It might be very small, but there's still a chance. So in this case, P is less than 0.001. That's a strong relation. Now notice the footnote does for the stars. If it's significant, you get either 1 star or 2 stars. In this case, it gets 2 stars because the p-value is less than. Not only is it less than 0.05, it is less than 0.01. So if it was more than 0.01 but less than 0.05, you get 1 star. Because it's less than 0.01, you're going to get 2 stars. That has to do with, again, we'll talk more about levels of significance and when we talk about p-values and alpha levels and all that sort of stuff. Okay, so I've got, let's see if I can clear this off here. I'm not going to worry about any of this. So I've got this stuff I'm going to worry. How many correlations do I have here? How many possible combinations of pairs of these 5 variables do we have here? 10. We got 10. Each little box, that lower triangle, means a different correlation. For example, the correlation between common sense and friends is here. 0.462, also highly significant. Strong positive correlation. Do you see anything that's not a significant correlation? Yeah. Academic intelligence and input relation is not significant because this number is not less than 0.05. Not less than 0.05. Okay, so I've got 10 correlations. Looks like probably 9 of them are significant correlations. They're all positive. Just that one of those positive correlations is not significant or is not strong positive. It's pretty close to it. I'm willing to take a 5% chance of being wrong, but I'm not willing to take a 5.2% chance of being wrong. That's, again, it's a line in the sand, but it's kind of a conventional line in the sand. Okay. I'm not going to go into it now. Well, I will too. Look at page 262. This is a good place too. 262 talks about how to make SPSS draw a scatter plot for you. You want to go through this real quick, or you just want to trust it? Okay. Well, let's do a scatter plot. Okay. To do a scatter plot, I'm going to go to graphs. Okay, you want to hear the next thing that doesn't make sense? We're going to go to legacy dialogues. I don't know why they call it that, but they do. When we get to draw graphs and curves and histograms and stuff, we're going to go to legacy dialogues. So I do what it says, go to legacy dialogues. And I want to do, oh, this part makes sense. I want to do a scatter or dot. Sometimes you call it a dot plot. I didn't write that name, but I'm going to do a scatter plot. So I click on that, and I get some options of what to click. And I'm going to click Matrix Scanner. I think you could also click Simple Scatter, but I'm doing what they say to do. I've got to define it. And again, I want all these values. I'm doing this pretty quickly, but you can go over again if you need to. It's spelled out here pretty closely. I'm going to put all those into my matrix variable box, and I'm going to click OK. And I'm going to get some scatter plots. Oh, I know why I clicked that one, because I'm getting a bunch of scatter plots, not just one of them. Processing is going to have to think about it for a minute. So there are my scatter plots for all 10 of them. Now again, I've still got the upper and lower triangle. So I am going to come on, Don. The upper right and lower left are, yeah, it's like a Rorschach test. What does this look like to you? It looks like a bat or something. I don't know. I'm going to just focus on the lower triangle because, again, one's a mirror image of the other. You see they're all positive. They kind of look sort of messy because you got such a large N80. You know, you got 80 dots, and the dots are pretty big. They look just kind of jumbled together. I think, was it this one that was not significant? They're in the same place they were with that with the correlation matrix a minute ago. They all kind of lean positively, but that was the one that leans less that way, even though it's pretty close to being significant. Now, the other thing, everything else is significant. You might not see that visually from the scatter plot, but because n is so large. The larger n is, the less the R value has to be significant. You don't have to remember that. SPSS is going to tell you that. Other thoughts, questions? I'll do one more example real quick. Maybe two if you want. Okay so far? Yeah, every time you can save an output window, which you may want to do for homework. And you can PDF that without a scan. You can just tell it to save as PDF. So you may want to submit that. Again, the other thing about homework when you submit it, yeah, if you're doing it on SPSS, yeah, I want to see your output window. I also want to see what the answer is. If it says, is it significant correlation, I want you to say, yes, it is, if it is. I mean, again, give me the answer. Don't just give me the output window. It's there somewhere. I need to make sure you can pick that out and interpret it correctly. So give me the answer. I'm going to close this out. And I'm going to do Lesson 31, Exercise 1. This is actually Exercise File 1. And if you look on page 264, you'll see the scenario is that Betty is interested in relating quality of teaching to quality of research by college professors. Oh, heaven forbid we do that. So I've got 50 professors over a 10-year period, and I'm evaluating on a 5-point scale for quality as instructors and quality of their courses. I average these ratings to obtain an overall quality rating. And the overall quality of course for each professor. Okay. In addition, we've also got the number of articles each professor published and the number of times the articles were cited by other publications. So rating 1 is their teaching rating. Rating 2 is the course quality rating. The third variable is the number of publications they have. Boy, this number 13 is a go-getter, isn't he? And then the number of times where people cited their publications in other publications is the last one. First thing we're asked to do, I'm asking to find the p-value between the correlation of a rating 1 and rating 2. If people rate you as an instructor high, do they also rate the quality of your course high? So I'm going to take these step by step. So I'm going to go to Analyze. I'm going to Correlate. Still by variable. Now this time, I only want the first two. So I'm going to select just the first two because I'm just going to answer this one part of the question. I still want it to get means and standard deviations. That's all I think I wanted to change. I click OK. I get an output window even though it hit it. And I am told that, do it again. So R equals 0.638. P is less than 0.001, meaning there's a strong positive correlation between you rating instructors and your rating of the quality of their courses. Let me show you something else we can do. What if I want to average rating 1 and rating 2, and I want to get an overall rating for both, a single rating for both quality of instructor and quality of course? Can I average these together, other than doing it for each line with my slide rule? The answer is yes. I just want to show you something SPSS can do. If I want to average, and the first line is averaging 4.87 or 2.78, I'm going to go to, what do I want to do? Oh, there it is. I want to go to transform. And we'll do some examples of that. I'm just going to introduce this concept right now. I'm going to go to transform, compute variable. Again, I want to average the two first ratings. And I'm going to call this overall rating. And by the way, you can't use any spaces here, like you can't use them when you're defining or listing the variables. How do I get the average of something? Not a trick question. Add them together and divide by 2, right? Okay, so I'm going to take the quality of instructors, add the quality of the course, whatever that sum is. I'm going to put those in parentheses because I want to do that first. And I'm going to take those and divide. Just hit the divide symbol like I could find it. Oh, there it is. It's the slash bar. I'm going to divide by 2. There are other ways to do this. For example, if I look at all and I can find there's a mean function down here. I'm just introducing this. I'll do it more later. I could find the mean and enter the two variables that way. But I'm just gonna mathematically add this to that and divide by 2. So if I click OK, look at what I'm going to have in my new data view window now. Yeah, anytime you do something, it gives you an output window that says, hey, I did something. I don't want that. I know it. I know it did something. I've got an overall rating of 3.83. That is the average of this rating 1 and rating 2. So I've got these overall averages. So I could combine variables like this. Can that work for you? So you can do anything pretty much mathematically with that transform option. Didn't work. What'd you try to do? Oh, shame on you having a legal character. Get the SPSS cops after you. Okay, yeah, that was going to be my guess. Student says, still have it? Before or after? Yeah, if you put a space here, it's gonna shake its finger at you. Say shame on you. Okay. Okay. So let's say, for example, I want this overall rating, including both the professor's rating as instructor and the rating of the course. I've got the overall rating. I want to correlate that to, say, the number of publications. Now I have this new variable I created. So I can go to Analyze, Correlate by vid. I'm going quick now. And by the way, when you go back to it leaves everything just like you had it before. I don't want this stuff anymore. I now want overall rating and number of publications. I've already got my means and standard deviation. No, my means and standard deviation needs to be selected. I'm ready to click OK to get an output window, and it turns out that if I look at the key part, which is right here, R for 49 degrees of freedom is equal to 0.322, and the p-value is 0.022. You know what? The better teachers tend to have more publications. It doesn't mean that publishing makes one a better teacher. It doesn't mean that being a better teacher results in necessarily more publications, but they go together. There's a significant because the p-value is less than 0.05. is positive because the R value is positive. There's a significant or a strongly positive correlation between the overall rating and the number of publications. You're rated higher, you tend to have more publications. You're rated lower, you tend to have fewer publications. So I do that part of this example to just show you how you can combine variables. Any questions? Yeah, the 49 comes from 50 minus 1, right? Correct. Okay, then what I wish for you to do, you'll notice by the syllabus says homework 2 is the Whit and Whit again. 6.9 and 6.11. And if you look at that page, those exercises, 6.9 and 6.11 are on page 149 and 150. And 6.9 asks you to do the correlation. Use SPSS to do that, please. Don't do it by hand like they would do it here. Don't do it like Whit do it. Do it like Green Sal can do it. Now, 6.11 is just kind of a, gee, what do you think about this question? So give that some thought, and again, submit your assignments on in the proper Dropbox. Any questions about the assignment or where we are now? Yeah, 6.9, 6.11, page 149, 150. Any questions here or home? If not, ready to close this section out. Okay. Let's see.